This video is about the value iteration algorithm, which is a way to solve the Bellman equation. So the Bellman equation is for this optimal value. The optimal value is the maximum over all possible actions you can take now from state S of what happens if you follow the optimal policy later. And this in turn can be written in terms of the value function. It's the expected value of the reward you get now, plus gamma times the reward you get after one step, given that you're in state S now and you play action A. So this is the Bellman equation. And we want to go from knowing this equation to solving for V. And of course, V appears on both sides. So it's some kind of system of equations that you want to solve. And the value iteration algorithm is the simplest possible way to solve for this. And here it is from the textbook. This is the pseudocode for it. I'll tell you, sort of very roughly speaking, what it does is it says we're not going to calculate V star in one shot. We're not going to calculate V star in one shot. Instead, what we're going to do is we're going to have a sequence. We're going to have a sequence of estimates for V star. Estimates for V star. And they're going to get better and better. So we're going to have the first one, the second one, the third one, and so on. And what is the sequence? Well, we have, we got a V star on the left. We got a V star on the right. What is the sequence going to be? So we're going to start off with some arbitrary guess, and we're going to update them. The next guess is equal to the expected value of the previous guess. So it's the maximum of A in A of S of the previous guess. R0 plus gamma V star of S. So use the previous guess to generate the next guess. Use the previous guess to generate the next guess. So, okay, I read it wrong. That's exactly about it. So we use guess number n, V star n, we use that to get V star n plus 1. And we're sort of just applying what's going on the right-hand side here. We're applying it over and over again. And we're hoping that if you apply it enough times, you get to a fixed point where it's sort of equal on both sides. And it doesn't settle down much. So I want to tell you, why you should hope that this works. Why is it okay to just apply the same thing over and over again? And I'm going to show you by what we did with Markov chains. So for Markov chains, we had the baby Bellman equation. Which said that when there's no actions to take, then there's no maximum. And so the baby Bellman equation tells you that the value at some state is the expected value, gamma times the expected value of where you go after one step, plus the rewards you get in one step. So it's exactly analogous to the same exact thing we have, but with no maximum. And you can just write this in terms of matrices. So this expected value, it's really a sum over all the probabilities. So maybe I'll actually write it out. Let's write it out. The sum over all possible S prime of V of S prime times the probability that S1 equals S prime given S0 equals S, plus some expected reward. I'm just going to write the expected reward on its own. The reward given S0 equals S. So this is for any given S, and this sum is really doing a big matrix vector multiplication of this probability transition matrix, the probability to go from state S to state S prime. That's the transition matrix of the Markov chain. So we're doing a matrix vector multiplication with the function V, if you think of it as a vector. So as vectors, this is exactly V equals gamma times the transition matrix P times V plus some reward vector, expected value. I'll call the reward vector R for rewards. So it was a matrix vector equation. And if you rearrange this thing, you can solve it exactly by using linear algebra. So, you can turn it into the identity minus gamma times P times V equals R, and you can try to solve it. Of course, it's not exactly invertible because there's some degeneracy. So often you need to take this equation and then also enforce V of, some states, maybe the values of V. That's what we did in class a while ago. But another way you could solve it is you could just apply this gamma p over and over again. So if you had the sequence, Vn plus 1 is equal to gamma p Vn plus r, and you just apply this over and over again, you will eventually get to a situation where they are exactly equal. And so the iterates Vn plus 1, the limit as n goes to infinity of Vn plus 1 equals V is the solution. So applying it over and over again works in the case of the Baby-Bellman equation. And why does it work in this case? In this case, it really is just linear algebra. And you could say it works because, and you can make an argument based on the eigenvalues of the matrix P. So this matrix P, there is a certain theorem, and we kind of briefly touched on it in class a while ago. It's called the Perron-Frobenius theorem. And this is the theorem that guarantees that there is a stationary distribution and things like that. And it says that the eigenvalues of P are all less than 1. So if you're doing this thing and you're applying the matrix P over and over again, then because all the eigenvalues are less than 1, all of the eigenvalues less than 1 shrink down to 0. And what you're going to be left over with is the eigenvalues of eigenvalue equal to 1. And that is the solution we're looking for. This is something to do with an eigenvalue equal to 1. Okay, so I won't go into super detail before, but I won't go into more detail than that. But so that is one way you can solve this equation, and we're going to do the same thing with a maximum. And it turns out that it works pretty well. So I'm going to show you a simple example using Pig of how this goes. So maybe I'll do one more little commentary on this pseudocode here. So there's a loop, and the loop is the number of iterations you want to do. So, I said keep doing it, and you can make this infinite sequence of guesses that are getting closer and closer to the real value. And the loop is how many iterations you want to do. And the way they do that in the textbook is they have some delta factor, and the delta factor is keeping track of how much you have changed from one iteration to the next iteration. And the idea is if you're not changing appreciably from one iteration to the next iteration, then we should just stop. So delta is keeping track of how much we've changed, and this line is updating it to make sure it's how much we've changed. This line is also a part of that thing as well. And we go until we don't change much. And this part, this is the line to keep your eye on. This is the one that is implementing the Bellman equation. This does the right-hand side of the Bellman equation. Okay. So that's the thing from the book. You're going to see an example. I think this makes a lot more sense with an example, so I'm going to give you one now.